Welcome back to ECE 501B. Homework number 8 is coming soon to a D2L website near you, and it will be this course website, 501B. Your project is actually due quite soon. I think it's 2 weeks from yesterday. I can't believe how quickly the semester flies, but the project is due then. Your final exam is 2 weeks from today? No, 3 weeks. 3 weeks from today. It's on a Monday. I did get the date right. It's a Monday, and the one thing that you will need to pay attention to is it does begin at 3:30 and not 4. But it will be a 2-hour exam and not 75 minutes. And it will start at 3:30 and go until 5:30, and we'll talk more about that later. There will not be an in-class lecture the next time we were scheduled to meet, but I will try to provide some content that you can watch or look at the notes or both. The ideal is that you do both. Today what I want to do is finish up polar decomposition. It's really a way of factoring a linear operator into a scaling piece and a direction piece. A square root of t dagger t, that's the scaling, that's a positive operator that we know has a positive square root, and then a matrix that does this direction finding or rotation between different spaces, and that's the isometry. We may get a little bit of introduction to singular values. I like that decomposition even more than polar decomposition. Polar just seems a little too cold for me, but singular value decomposition is a very powerful decomposition, and we'll talk more about that. Probably, maybe that's what I will talk to myself about on Wednesday when I'm recording that lecture. Again, no in-class lecture on Wednesday, so don't spend your fuel coming to campus unless you need to come here for another reason. Okay? Here is really where we left last time, was with the statement of the theorem, 741, and that is if you have a linear operator t on some complex or real inner product space, then there exists an isometry S such that t can be broken into two pieces, a magnitude or scaling piece and a rotation or a direction piece. And let's see if, in working through some of the ideas in this proof, if it doesn't become a little bit more clear that we can do this or that this is possible. First, we're just going to assume that we have this linear operator that we're calling t on the given vector space. And now let's assume that we have an arbitrary vector v in that inner product space. Then it's possible to form the norm and square it of t, that linear operator applied to that arbitrary vector v. And we know another way of rewriting the norm squared of a vector in terms of an inner product. This can be written as that vector inner product with itself. And now we can start manipulating with this inner product expression to come up with a piece of this particular relationship about t and its factored form. S again is just a rotation. It's an isometry. That does not change the scaling of this map of S separate or S times some other piece. So it would be nice if what we're trying to do is show that the norm of t is the same as the norm of the square root of t dagger t. That's what we're trying to show in this first piece. Then we're at least preserving the scaling in this factorization. That's what we're trying to show now. And to do that, we're simply going to play with some of the properties of this operator t and the inner product. Now we know that the adjoint of an adjoint is equal to the original operator, which allows us then to rewrite this as t dagger dagger v. I haven't done anything there other than to use that equality that t dagger dagger is t. And now I can move that operator from the second slot into the first slot. And that means that since I already have the dagger applied to what's in parentheses, I can simply put that parenthetical operator in front of the first slot vector. Meaning this is now equivalent to t dagger times tv v. That's just from the definition of the adjoint. The adjoint is the operator that we need in order to allow us to slide it from the first slot to the second slot. That's the definition of the adjoint, and we're just doing that in reverse here. Now that we have this t dagger t, that has what kind of characteristic? T dagger t. It's a positive operator, and so now we can factor that into a square root, or write that positive operator as the product of two square roots. So that now t dagger t can be written as the square root of t dagger t, with the no understanding that the square root of t dagger t, what that means, that's just the positive square root of this matrix t dagger t, or the operator, times the same thing applied to v. And that comes to us from Theorem 27 and Proposition 28 in Chapter 8, dealing with the square root of a positive operator. And in this case, it's the square root of t dagger t. Now that we have that, we know that this square root of t dagger t is self-adjoint. And now let's just apply the adjoint definition again, knowing that the square root of t dagger t is self-adjoint, meaning we don't really need to show the dagger on that operator. Or we now have the square root of t dagger t times v. Now I'm moving that first operator in the last equation to the second slot, and since it's self-adjoint, I'm not going to show the dagger on it. Again, that's just the adjoint definition, but now this is the piece that we wanted. We can now write that as the norm squared of the square root of t dagger t times v. And that's what we were setting out to show, that we're not changing the norm between the linear operator t and the square root of t dagger t. We're preserving the norm. So the square root of t dagger t has the same effect on norms as t, and that's what we want. We want them to be doing the same scaling. That's good since since the other piece of our factored form of t, which was s, that we wanted to be an isometry, and if it's an isometry, the isometries don't mess with the norm, or they cannot adjust the norm. Which allows us to conclude then that the square root of t dagger t in the factorization is really doing what we want, is going to work the way it is supposed to work. But now we need to see, is there actually an S? We've sort of concluded that we've broken it into two pieces, this linear operator. And the one piece, well, we now know that the pieces work properly relative to scaling. The isometry piece isn't going to scale anything, and the square root of t dagger t does. Now we need to say, but is there an isometry that will work? Or is there such an S? And the idea is that we sort of are doing this in two pieces. We are going to create an S1 such that the range of the square root of t dagger t is going to be mapped into the range of t, because we didn't say anything about t being surjective. And so now we kind of have to do this in two steps, this creation of an isometry. We've now have this square root of t dagger t in our factorization, but we need it to be rotated or redirected to give us t, and the operator that we're going to use is this S1, this isometry. Then what we will do is we will expand or extend S1 to an isometry S, meaning all of the, let's say, piece vectors or direction in our underlying vector space that are not in the range of the square root of t dagger t, they're in the orthogonal complement of the square root of, or in the orthogonal complement to the range of t. We also need to map those into the vector space capital V. And we'll do that by extending S1 in an orthogonal direction. All right. So if that's the idea, the very first thing that we are going to do is define or build or create an S sub 1. So we're going to just define a map S1 that takes the range of this square root of t dagger t into the range of t. Meaning we are simply saying that we are now defining a map, S1, such that when operated on the square root of t dagger t and v, that's just a vector now, that is to be defined to be equivalent to t operating on that same vector v, where v is any vector in our underlying vector space. This is simply the input to S sub 1, this isometry, and this right-hand side is the output of S sub 1. So now, whatever the square root of t dagger t is, that may not be preserving the range of t, and so we're having to rotate it through this isometry S1. The square root of t dagger t simply allowed us to do the proper scaling. Now we need to basically rotate whatever that gives us back into the appropriate range space of t with this isometry S sub 1. The hope here is we can extend S1 to an isometry meeting our needs for S. Meaning S1 is just working on the piece of this entire vector space capital V that corresponds to the range of T. And if the range of T is not, or if the linear map T is not surjective, that means it doesn't cover the entire vector space V. We need to make sure that we fill out S1 or extend it so that the entire isometry is working on the entire space, capital V. All right. We are wanting to end up with an isometry S, the full thing. And when we say something like S square root of t dagger t equaling t, we're meaning that S square root of t dagger tv is equal to tv for all vectors v in the inner product space V, whether that's complex or real. Now we know that S1 has been selected to meet this. That's how we defined S1. We now need to make sure that whatever we do to S1 to extend it to S, to make it, let's say, more encompassing of the rotation that's needed, that we do not violate this condition. So we're not going to be putting something that's maybe in the orthogonal complement to the range of T into the range of T when it shouldn't be there by this isometry S. What we want to do is see if this S1 that we've defined is even well-defined, or a well-defined linear map. But well, I should say that S sub 1 up here has been defined to make this S square root of t dagger tv equal to tv. That's how we defined S1. But now does this make S sub 1 a well-defined linear map? First, let's check the uniqueness of the map itself. So let's now check the uniqueness of the map. Here's our statement. If the square root of t dagger t v1 is equal to the square root of t dagger t v sub 2, then we actually want tv1 to equal tv2. That's our statement for uniqueness. If we start with the square root of t dagger t v1 equaling the square root of t dagger t v2, then we want tv1 to equal tv2. Here's our proof of that statement. Let's look at the norm of the difference between tv1 and tv2. By the linearity of the map, we know that that's equal to t times v1 minus v2. But somewhere up above, right here, we showed this equivalence of norms. We had TV, the norm of that is equal to the norm of the square root of t dagger tv. Now we have v being replaced by another vector, which we're calling v1 minus v2, but now we can use this relationship because of what we know about this linear map t. So this from above is equal to the norm of the square root of t dagger t times v1 minus v2. Where we were actually showing that the norms were preserved in that relationship. And now we can simply start playing again with, the linearity underneath or inside the norm. We can now say that that's equal to the norm of the square root of t dagger t v1 minus the square root of t dagger t v sub 2. But that was actually our hypothesis. We said if square root of t dagger t v1 is equal to the square root of t dagger t v2, then if we subtract the right-hand side from both sides, we end up with the 0 vector, and the 0 vector's norm is equal to 0. So this is true from our hypothesis. And now we've shown that the right-hand final expression, the 0 vector, or 0 in this case, since it's on a norm, is the norm of tv1 minus tv2, which means what's inside the norm is the 0 vector, and that then allows us to conclude that tv1 is equal to tv2 when the square root of t dagger tv1 is equal to the square root of t dagger t v sub 2. We now have a uniqueness of our map. Let's now check the linearity. What do we have to check when we're checking linearity of a map? Sort of a review for the final. Pardon? Additivity and homogeneity. So let's do homogeneity first. Which says that now we have S1 operating on the square root of t dagger t and let's say now that's AV. And by the definition of S1 square root of T dagger T AV, we said that has to equal T operating on AV. That was how we defined S1. So this was the definition of S1. But we know how the linear map T operates on a scalar inside its, so this is now equal to ATV. And now if we just apply the definition of S1 again, this is now A times S1 square root of T dagger T V, and now that shows that homogeneity is satisfied. If we look at additivity, it follows sort of this same idea. We have S1 square root of T dagger T V1 plus V2. By the definition of S1, that's T V1 plus V sub 2. But that's simply TV1 plus TV sub 2, and that now, using the definition of S1 again, is S1 square root of T dagger T V1 plus S1 square root of T dagger T V sub 2. And that's now the additivity that we wanted to show. So that particular map is a linear map. Now, if we look at what 742 and 743 tell us, we can now say that S1U, the norm of that, is equal to the norm of U for all U belonging to the range of the square root of T dagger T. We can step through that. 742 was basically that the norm of TV was equal to the norm of the square root of T dagger TV. And 743 was that S1 square root of T dagger TV was equal to TV, which now allows us to just sort of play with those together. If we look at the norm of TV, we know that from 743, that's the norm of S1 square root of T dagger TV's norm. But now from 742, the left-hand side is equal to the top right-hand of the 742 expression, which is now the square root of T dagger TV, and those two right-hand terms tell us something about S1. Now S1U's norm is equal to the norm of U, which is what we were wanting. So here is our U in both the middle and the right-hand side, where we were really sort of playing with this relationship being 743 and these equalities being 742. And since S1 is injective, because of this norm relationship, then we know something about the dimensions of the range of T dagger T and the range of T. Meaning, if I wanted to say I have the dimension of the range of the square root of T dagger T as a value, that's actually equal to, since S1 is injective, we're not allowing any vectors to sort of hide by getting mapped into the origin or the zero vector, so that now this dimension is the same as the dimension of the range of T. Now, if we have basically the same number on the left and the right for these dimensions, and V hasn't changed on the left or the right, V being the underlying vector space, now we know that whatever is in the orthogonal complement on the left must be the same dimensionally as what is on the orthogonal complement of the right. Meaning now we can say, therefore, the dimension of the range of, hopefully this is somewhat clear, the T dagger T, and let me put that in parentheses so I can do the orthogonal complement. So the perp of the range of the square root of T dagger T, its dimension, is equal to the dimension of the range of the orthogonal complement of T. And if that's the case, we can find orthonormal basis for those two spaces. The perp of the range of T dagger T and the perp of the range of T. And let's do more than orthogonal. Let's do orthonormal. So now we have orthonormal basis on the range of the square root of T dagger T perp and the range of T perp. And those bases have the same length. They're the same size. With that understanding, then we can simply parameterize those bases. Let's now choose E1, E2, up to E sub m to be our orthonormal basis on the range of the square root of T dagger T perp. And then F1, F2, how many of these do we have on the range of T perp? What's our subscript on the F's? M, Michigan, if it's the same length as the orthonormal basis on the range of T dagger T square root perp. So this is now, we now have two, and they are not necessarily the same, but they are the same length. What we want to do now, here's where we extend our isometry. What we want to do now is define another map. Let's say that's S sub 2, where we now have A1, E1 plus A sub 2, E sub 2 up to A sub M, E sub M. And we want that to be the same scalars, A1, F1 plus A sub 2, F2 plus dot 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 plus A sub M, F sub M. We're just defining S sub 2 to do that rotation. We can pick, or we found these orthonormal bases, E1 through EM. We found the orthonormal basis F1 through Fm based on knowing the orthogonal complements to the range of square root of t dagger t and the range of t. Now what we want to do is define a new isometry, S2, that will rotate this vector of e's in some scalar combination into another vector, but using the same scalars to weight those orthonormal bases. And now S sub 2 is, we're defining another map, S sub 2, from the range of the square root of t dagger t perp to the range of t perp, and we're using the same weighting coefficients A1 through A sub Michigan. The weighting coefficients are the same. Now that we have S1, that's defined by rotating the range of square root of t dagger t into the range of t. And we have those two spaces, we can find their orthogonal complements. We use their orthogonal complements to find basis, orthonormal basis for those orthogonal complement spaces, and then we define a new isometry with this particular structure, or using this relationship. Now that we have S1 and S2, and they're basically working on two orthogonal, or direct sum, it's a direct sum decomposition of the underlying vector space V in two different sort of ways, with the square root of t dagger t and with t. Now what we want to do is define S. Now define the operator S. That is S1 on the range of the square root of t dagger t, and it's S sub 2 on the orthogonal complement to the range of t dagger 2, t dagger t. And because they're a direct sum decomposition, S is really just the sum of S1 plus S2, those isometries. Because there is a direct sum relationship between the range of the square root of t dagger t and its orthogonal complement, then any vector v in our underlying vector space capital V can be uniquely written as V is equal to U plus W with U being the piece of V that's in the range of the square root of T dagger T, and W is the piece of V in the orthogonal complement. And now we can look at S applied to V. S applied to V is now simply S1U plus S sub 2W. Since S1 is only working on the vectors in the range of the square root of T dagger T, and S2 is only working on the vectors in the orthogonal complement. Now that we have that, we can consider our factored form of the original linear map T relative to this new factored form, the polar decomposition, S square root of T dagger T applied to a generic vector V. So now this is S square root of T dagger T V and this particular vector inside or that's being operated on by S, where does that particular vector live? By definition, let's say, of the square root of T dagger T, where can we get to from any V? Maybe that's a vague question. But if I have a map and I operate on some vector with that map, where can I get to? The range. So what's in the square bracket is falling in the range of the square root of T dagger T. So this is now this is a vector in the range of the square root of T dagger T. But what do we know about vectors in the range of T dagger T in terms of our decomposition? That's now what we were calling U, isn't it? And so we know that the only piece of the right-hand side of SV that we will end up with when we operate on some vector V is the piece that is associated with the vector inside the range of the square root of T dagger T. Meaning S square bracket is equivalent to S1 square root of T dagger T V. But how did we define that? We defined S1 to be T V. So our decomposition works. S times some vector is equal to T times that vector. So that now we can say that our decomposition works for all V in our vector space. because it maps it into where we want it to map. Because really what we're doing is this is now our factored form of the matrix. We've now factored T into this S square root of T dagger T, and we're applying that to V. We want that to be equal to capital TV. And that's how we defined S1, and that's how we built up these different decompositions. Now what we want to know is S, after we've extended it from S1 including S2, is it truly an isometry? We know that it gives us, for any V, this decomposition works, this particular way of rewriting the matrix T. What we want to do now is ask, but is this S an isometry? Now what are we looking to do? We're really wanting that to be equal to V squared, aren't we? The norm of V squared. But this is, by definition of how we've built up S, this is now S1U plus S sub 2W, where U and W are decomposing V. We've learned that that norm squared can be written as an inner product. And now we can simply look at the additivity of the different slots of our inner product. We have the first term in the first slot and the first term in the second slot, plus, let's say, the second terms in both slots. Then we also have, doesn't really matter which order I do this, we have the first term in the first slot with the second term in the second slot, and the second term in the first slot with the first term in the second slot. But what do we know about S1U, S2W, and S2W, S1U? S1U stays in U, doesn't it, or in the appropriate range of the square root of T dagger T. S2W is in the orthogonal complement, and it stays there. It starts there and stays there because of the way we defined S1 and S2. Since this first slot and second slot in, let's say, the third term in that expansion are orthogonal, we know that this piece goes away. The same argument allows us to say that this fourth term in that expansion also is 0. And now we can say that what we started with, which was SV squared, is equal to S1U squared plus S sub 2W squared. Now we have just a little bit more to do, but what do we know about S1 and S2? They were by themselves isometries, so they're norm preserving. S1 and S2 are isometries by construction. which now allows us to say that the left-hand side is equal to, I'll just rewrite it, S1U1 squared plus S sub 2W squared. But now that we know that S1 is an isometry and S2 is an isometry, and we know by the way that U and W were built, they were orthogonal, so the Pythagorean theorem is true, which now allows us to say that U's norm squared plus W's norm squared is equal to V's norm squared, and that's what we wanted to show, that S indeed is an isometry. Let's sort of talk about what we've done with all of this. We now can say that any linear operator, which we're generically calling capital T, so any linear operator can be decomposed since it can be decomposed, it's sort of green. That's why I'm using the green. Sorry, that's pretty lame. But maybe you'll never forget that decomposition, polar decomposition. So you have to go kind of north maybe for this decomposition. But any linear operator can be decomposed as a product of an isometry and a positive operator. And if you sort of forget that, just remember complex numbers. Complex numbers you can write in polar form. And that's really what we're generalizing here. The idea of breaking down a map into a rotation or a direction piece and a scaling piece. We can understand how these classes of operators work meaning we know how the scaling works and we know how the rotation works, so we can apply that insight to gain knowledge of any general operator. Meaning an operator, as basic as it can be, is it's scaling and rotating. That's how you can think of any generic operator. Now what you need to keep in mind, note that bases where these operators have nice representations meaning the basis for the rotation and the basis for the scaling may not be the same. Note that the basis where these operators have nice representations may not be the same. Meaning we may not be able to represent the scaling in a nice diagonal form with the same basis that we might be able to see this rotation in a nice way. Can also, this factored form can also be viewed as a statement like polar representation of a complex number about matrix factorization. We were talking about operators. Now we can look at their matrix representation, so that any matrix, and sometimes I get sort of caught up in thinking of them the same way, but we were just talking about operators. Now we can think of their matrix representation. Any matrix now can be factored into two matrices. One matrix in this factored form, one matrix factor, has eigenvalues. If this is the rotating one, what are the size, or can you say anything about its eigenvalues? One matrix factor has eigenvalues with magnitude equal to 1. That's the rotation one. That's the rotating matrix factor. And one matrix factor has non-negative eigenvalues. So we can have 0 eigenvalues, and we don't have to worry about the signs in that second matrix factor because we can flip them 180 degrees. We can rotate those with the first factor if we need to sort of change the direction, change the sign of that particular matrix. Yes?
So for the polar form of complex number, you have the rotation occurring first and scaling, right? Whereas with this, it looks like the scaling is first.
So the comment is, in complex numbers, you can scale. Actually, since it's a scalar, it doesn't really matter which way you, to me, you can think of a complex number having the real, or a magnitude and an angle. And I don't really think it matters which order you apply those. Yet in the matrix form, it is important to keep track of the way that we order the operations in a matrix. And so what we're doing is we're scaling first with the square root of t dagger t, and then we're rotating after that. But in the scalar case of a complex number, it really doesn't matter to me whether we rotate and then scale or scale and then rotate. I don't believe. You can always have, it's just a scalar, so you can sort of slide those. They commute is what I'm saying in terms of the rotation and the magnitude of a complex number. Yes? So now you want to, the question was, I think, why does order matter maybe with matrices? I think the way we have built it up, we needed to sort of think about worrying about range space first and then rotating relative to the scaling piece. So we may have been able to do it the other way, but it really doesn't seem as clean to me to do it the other way. It seems cleaner to scale and then rotate, but I haven't thought about doing it the other way, to rotate and then scale. But the way that it's presented in this book, in the polar decomposition, is we want to scale first and then rotate, matrix-wise or linear map-wise. So in the polar decomposition, I don't know if that answered your question or not, but I don't think the order with which we rotate and scale for the scalar case in complex numbers is critical like it is in the matrix or the linear map stage. But in the polar decomposition, the positive operator is this square root of t dagger t. And in fact, we call the eigenvalues of this map, or if it was now a matrix and we were looking at the matrix of associated with the square root of t dagger t, we call maybe it's a good thing we're skipping the lecture on Wednesday. You are, I'm not, but you can watch it whenever. We call the eigenvalues of the square root of t dagger t the singular values of the original operator t. And we can take a few things from that. We know something about the square root of t dagger t relative to its behavior. The square root of t dagger t is a positive square root. So since the square root of t dagger t is positive, then we know something about the sign of the singular values. The singular values of the linear map T are always non-negative. And we could have repeated eigenvalues of this positive matrix. We repeat each eigenvalue relative to the size of the null space. So we repeat each eigenvalue, the dimension of, the null space of the square root of t dagger t minus lambda I. We need to know how big is that null space dimensionally. Is it one-dimensional? Is it two-dimensional? If it's one-dimensional, we will have one eigenvalue for associated with that eigenvalue. And if this null space is bigger than 1, then we'll have repeated eigenvalues of the square root of t dagger t. So let's look at an example that starts to illustrate this concept of singular values. Again, these are a way to think of the size of a matrix or a map. Example 745. Suppose that we now have a linear map And hopefully I will remember to use Z's. I guess I usually don't like to use Z's because it may induce sleep at this time of the day, but I might revert to X's. But here we're working with a four-dimensional linear map, and we're saying that that T, that linear map, now maps Z1 through Z4 into 0, 3Z1, 2Z2, and minus 3Z4. Now, as a review for the final, what's the matrix representation of that linear map T? Or what, when operating on this, I like to view them in columns, Z1, Z2, Z3, Z4 stacked from top to bottom, will produce, another vector stacked on top to bottom, 0, 3Z1, 2Z sub 2, minus 3Z sub 4. First, what are the dimensions on that matrix representation of that linear map T? 4 by 4. It's going to be square. And the very top row of this matrix representation is supposed to generate a 0 in the first coordinate of our output. That one's easy. It needs to scale everything with zeros. The next row now just needs to pick off one element in the column of Z1 through Z4 and scale it by 3, and it's actually picking off the first coordinate, which now allows us to put a 3 there and nothing everywhere else. The third row. Now I'll let you do that. What's in the first column of the third row? 0. The second column, 2, 0, 0. What about the fourth row? Where do we have any non-zero entries? It's the very last one, and this one should be minus 3. And there now is our matrix representation of the linear map T. I think we're good on that. What is the before we continue, what are the eigenvalues of the matrix representation of T? There's only 2 distinct eigenvalues, aren't there? There's 4 eigenvalues, but there's only 2 distinct. 0, 0, 0 is repeated 3 times, but we only have 0 and minus 3 because this matrix is lower triangular, isn't it? So our eigenvalues are all on the diagonal. 3 of those eigenvalues are 0, 1 is at minus 3. Those are the eigenvalues of our linear map. We are interested in the singular values, not the eigenvalues, because we already said the singular values can't be negative. So this is not the singular values. These are the eigenvalues. What's the matrix representation of the adjoint of T, or T dagger? Now I slid that off, but it's just the transpose of that. If we transpose that, the first column becomes all zeros, and I'll fill in the rest. Then we have a 3. Then we have a 2 in the 2, 3 entry, and we preserve that minus 3 in the 4, 4 entry. And now if I ask you on the final, if I was feeling like providing gifts, we have T dagger of Z1, Z2, Z3, and Z4 producing what, let's say, row vector. which I like to think in terms of columns. But now what's in the first entry? 3z2. Is that okay? That's now the adjoints map of our linear map T. We can now look at the matrix representation of T dagger T, which is really just the product of the matrix representation of T dagger and the matrix representation of T. That I will let you sort out at home if it's not clear, but it's actually a pretty nice looking matrix in terms of its structure, because it's a lot of zeros and it has all its non-zero entries on the diagonal. And now if I wanted to, I could say, what's this linear map associated with T dagger T? Nine Z1, 4Z2, 0, and 9Z4. This one's pretty clean, isn't it? To find now the square root of that particular linear map. Because it's diagonal, it's pretty easy. Now we just take the positive square root of each of those coefficients. We have 3z1, 2z sub 2, 0, and 3z sub 4. And now what are the eigenvalues of T dagger T square root? Well, I'm going to order them from highest to lowest, because a lot of times that's what happens when we do singular values. We order those from largest to smallest, but here we're just identifying the distinct eigenvalues of this new map, square root of T dagger T. And now that we know the eigenvalues of square root of T dagger T, and from this particular statement, we call the eigenvalues of the square root of T dagger T the singular values of T. You can now tell me something about the singular values of the original linear map T. But now we need to account for the repeated nature of those eigenvalues. If we went back to the eigenvalues of the square root of T dagger T, 3 is repeated, isn't it? And if we subtracted minus 3i from that matrix, we will get a null space that's two-dimensional, meaning we are going to have two different eigenvalues associated with 3. The eigenvalues of, the singular values of T are 3, 3, 2, and 0. And what were the eigenvalues, just for completeness, of T when we first started? Minus 3 and 0. So the scaling is there, but now we have singular values of T, which gives us something more about scaling. Eigenvalues of T, depending on the context of what you're dealing with, you can interpret differently than singular values. But singular values are going to tell us about the scaling nature of our linear map or of our matrices. And I will pick up on Wednesday. You can pick up whenever, but do it before next week, and I will see you a week from today, physically.